Good morning, everyone. We're now starting this session. It is a pleasure for me to introduce Roberto Alvarenga from Next Media Preto, dear friend and colleague, and he's going to talk about artificial curves with prescribed normal traits. Roberto.
Thank you, Pietro. Thank you, everyone, for coming. Thank you, the organizers, for this amazing conference. It's ever a pleasure to be back in São Carlos, to see too many friends, as Pietro. Today, I'm going to talk about this joint work with Erivelto Borges, which is concerned about artificial curves with prescribed normal trace. This is a name that I give to this kind of curves that will be clear during the talk while I'm saying with prescribed normal trace. Okay. Let me fix the notation for the whole talk. We'll be concerned with the following data. I'm going to take A and B on Fq and consider alpha and beta on an extension of degree n of Fq, such that the norm of alpha is A and the trace of beta is B. And with these elements, I'm going to consider this curve. This is our arc-in-trial curve. It's in the title of the talk. Okay, it's the curve given by this affine equation on A2 over its. Nice to say that it's defined over extension of degree n of Fq. And by x bar, I'm going to denote its projective closure on P2. Okay, this is the main object of this talk. Okay, and in a few minutes, I'm going to try to motivate you why study this artificial curve. But before, let me give you some very easy properties of this curve. It's a non-singular curve, and since it's a plane curve, non-singular, the genus is very easy to compute, right? It has just one point everything. In other words, the number of rational points on x bar is the number of rational points on x plus 1. And the famous Hasse-Weil bound for x bar is given by this inequality. Okay, just put in the formula of Hasse-Weil bound, the genus here, and we got this. We got the Hasse-Weil bound for x bar. Okay, what's the goal of the talk? The goal is improve the Hasse-Weil bound for this arc-in-Schreier curve. Okay, improvements on Hasse-Weil bound is always very interesting problem on algebraic geometry over finite field. But we do have one more reason, or more than one reasons, to try to improve this the Hasse-Weil bound for this curve. I will tell you in a moment. Okay, so this is our curve, and the goal is to improve the Hasse-Weil. Okay, so why should we care about this curve? If it's not enough for you just to improve Hasse-Weil bound, I will give you more reasons. The main reason which I can connect to this curve is the following. Consider, given A and B on Fq, the number of elements on Fqn such that the norm is A and the trace is B. Okay, I'm going to denote this number by NNAB. Okay, what about the bounds or even explicit calculation of this NNAB? Okay, the connection between the arc-in-Schreier curve and this number is the following observation, which says the following: if B is non-zero, the number of elements with given norm and trace are given in terms of the rational point on x And the same holds if B0, just have to take off a Q factor on the number of rational. So if this theorem, like an observation that follows from Hilbert-Lein's theorem, we had a connection between our Artin-Schreier curve, which was, just to remember, let's give you the following. And the number of elements with given normal trees. So with this connection, one improvement on the number of rational points will give us hopefully one nice bound for the number of elements with given normal trees for this NNA. Okay, this is a motivation. So if you are not enough sufficient with this motivation, I can tell you more reasons to study this curve by studying this NNEB, which is the following. Why should you care about this number of elements with given normal trace? Well, this occurs in the work of in the 90s, the work of Nicholas Katz, where he was interested in these Soto-Andrade sums. I'm going to come back to this work in a moment. It also, the developer has observed some time ago that this number is connected with the genius of certain Frobenius non-classical curves. So as I think it was said several times this week, Frobenius non-classical curves are prototypical of maximal curves, and as I pointed there, this number is connected with some Frobenius non-classical curves, and we have a connection with parabola theory, for example. So one more reason. Another more arithmetical reason to study this number, it's connected with the number of reducible polynomials with given normal trace. And another more reason, which is equivalent to this problem here, is to study these reducible and monical polynomials in this arithmetic progression. Okay? One last reason to study this number, it's for n equals to 3. It was applied to prove the existence of cubic primitive normal polynomials with given normal trace. Okay? So this is a series of motivations why you should care about this number. As I showed to you in the last slide, since it's connected with our Artin-Schreier curve, then this gives us motivation to study our curve. Okay. So let me just tell you what I'm gonna tell you in a minute is the following. So we have the curve. We have the connection between the rational points on X and the number of elements with given normal trace. We had before no bounds for the number of elements with a given normal trace. So I will present to you these known bounds for the number of elements with given normal trace, and then by given new bounds for the Artin-Schreier curve, I'm going to improve these bounds which I will present to you now. So what was known before for NNAB? As I said, Katz has studied this number, okay? And by applying Klosterman sheaves, we got given this bound for NNAB. After Katz, in 2010, Moiso and Wan, they provide this improvement on Katz bound, okay? Their strategy was connect this number here, with some Toy-Labial variety that I will tell you afterwards. And then by calculating the homological calculations and using the left shift trace formula, they have provided this uniform improvement for cat's mouth. And more recently, Gao, Cooper, and Wang, by recursive strategy, they had provided this bound for the number of elements with given normal trace, which, roughly speaking, improves Moissan bound when n is bigger than square root of q.
What's D there?
Sorry?
D.
Oh, D is the GCD of q and n. Q minus 1 and n. Okay, sorry. Okay, so this was what was known before. And what is our approach to the problem is the following. So if you have in mind improvements for the curve, we'll give you improvement for our hopefully improvements for the number of elements with given normal trace. The first new that I can tell you now is the following. Take X, our arbitrary curve. Oh, here's D, the definition of D. When trace is 0, trace of beta is 0, beta is the constant here. We have this improvement for Hasselbalch bound, okay? But we can do a little bit more, which is the following. For Q be odd and N be even, we can actually state this improvement for Hasselbalch, okay? Where S alpha here is just in terms of alpha and the quadratic character of the schema. Okay, so both of the bounds here improve Hasselbalch bounds, okay? Hasselbalch bound for X. Okay, so what's the situation if the trace is non-zero? If the trace is non-zero, we do have also improvements, but here we can split the improvements where n is bigger than square root of q, and when n is smaller than square root of q. Okay? Both of these are also improvements on the Hasselbalch bounds. And as in the situation when the trace is 0, we can also do something better when Q is odd and N is even. We do have this better bound for the number of rational points on X. Okay? But now we get this term which depends on alpha and beta. Okay, so with this, I have just shown you that we can do a lot of improvements of Hasselbalch bounds, okay? Especially in the case of when Q is odd and N is even, we can do a really nice improvement on Hasselbalch bound. When I say really nice improvement on Hasselbalch bound, I can say that this will give us improvements on the null bounds for the N and A. Okay, I mean the number of elements with given normal trace. Okay, what can we get from these improvements is the following. The first one is, as I just said, it's an improvement for the null bounds for the number of elements with given normal trace. Okay, we do have these two situations when B is 0 or not. We can write this bounds for N and B since, as I told you in the beginning of the talk, we have a connection between this number here and the number of rational points on X. Okay, and both of the bounds improves the previous bounds in this situation when Q is odd and N is even. So roughly speaking, we do have an improvement for half of the case, right? More applications. As I said, Moissan and Wang, they did the calculation of this number here by connecting to some theoretical variety. So what do we get if we use our bound for the number of rational points on X, applying to this toric Calabi-Yau variety? So precisely, this is the toric Calabi-Yau variety hypersurface considered by Moiso and one later work. Okay, and if we apply our method by connecting to this nice arbitrary curve, we get this bound for the number of rational points on the toric Calabi-Yau variety. Okay, which gives us an improvement for Moiso and Moiso. They do have a bound for this hypersurface, but using our bound, we can get an improvement when n is bigger than, roughly speaking, bigger than square root. Of course, you can ask me what's the situation when q is odd and n is even. We also have improvements on that bound. I mean, because before, I am considering this q odd and n is even, but here I just put the general case. But if we consider q be odd and n be even, we have better bounds for this toric Calabi-Yau variety. Okay, this is another application of our method, and to finish the talk, I mean, we can, as I said in the beginning, this number, this NNAV, the number of elements with given normal trace, they are connected with several things that I told you in the beginning. One of them is the number of reducible polynomials with given normal trace. We can also apply our method to improve bounds there too. I didn't put here, but we can apply to all the situations. With our improvements, we can get improvements on that situations too. And to finish the talk, we can actually calculate explicitly the actual number of rational points on X for small q's and for arbitrary n. Okay? By doing that, for example, for the case q equals to 3, we have the following. I will state the application in terms of the number of elements with given normal trace. But you should know that behind of it, I'm actually calculating the number of rational points on X and using the correspondence between these two numbers. Okay. So as for example, if Q is 3, we can actually provide the number of elements with given normal trace, which does not depend. I mean, which holds for every n. Okay. But we do have this kind of identities for Q equals to 2, 3, 4, and 5. Yeah, I think that's all. Thank you for your attention.
Thank you very much, Roberto, for this very nice talk. Are there any questions, remarks?
Very nice talk, very interesting. So you bound the n and the b, and then using that we bound the number of points of X. And
No, the opposite. We did. We actually did. This is why I tried to say that what's important here is the curve. Is this arbitrary curve? We did the improvement on Hasselbeck, and then we got the n.
so okay, so my question makes more sense.
Thank you.
Yeah, I had a question. Thank you for the talk. So your results for NAB and the CATS result and the Moisio one, they're intervals, right? So
Yeah.
number minus something less or equal to
Yes,
something.
yes.
But the center of the interval is not the same.
It's not the same. Yeah, you are.
So,
but
can you draw a picture of where the intervals are? I mean, I want to get an idea of how much of an improvement it is, which side, you know. So the center is the same. So it's like this and like this, or you know, sort of do they overlap or
it's not the same. But if we we had compared these amounts and
there's one interval is inside the other because, like for example, the cat's interval, the center of the cat's interval is different from the center of the other interval.
Is different, right?
Yeah, the center is different. So,
but here in Moisio 1, the improvement is for N, Q, and M.
Yeah. But I'm sort of curious, and then you have a different bound with a different center.
With a different center, yes.
Yeah. So,
yes. But it's okay. But it's
how do they fit? I
mean, you are right. It's a different center, but.
It's okay, I believe that it's an improvement.
Okay.
I'm not saying it's not an improvement, I want to see the picture. I mean, it's like their interval, their interval is like this and yours is like this, or yours is close to the middle, you don't have to answer that, but I think it's a suggestion that you should draw a picture of all these intervals.
Okay. Yeah.
So that people can visualize better. So it's not just the length of the interval. You have a shorter length, but you have a different center. So.
Okay, I see. Yeah. It's nice to have.
Thank you. Any more comments, remarks? I have just a curiosity about the techniques you use to bound the number of points of the curve.
Oh, for x, just exponential sums.
Oh, I see.
Yeah. Just an interpretation of the rational points in terms of exponential sums. And it's kind of finite solution.
So a lot of complement. A lot of complement.
Yes.
I mean, it's very interesting. So nice work. Any more comments, remarks? Well, if not, let's go back. We're assuming 2 minutes. The talk will be pre-recorded.
Eu nunca pensei nisso, mas porque na hora de comparar,
Mas se você fizer um desenhozinho, aí você está dizendo se o intervalo está dentro do outro, mas os outros dois não têm o mesmo centro, talvez tenha uma interseção. O intervalo do coisa está dentro, do intervalo do cara, então.
projection, in other words, BF is Q. So our work in this subject is published in two parts. The first part is a theoretical aspect we published 2 years ago in IDMD. And today I will focus on the second part, is the computational aspect and application that is published officially this year in Mathematical Computation. And I also present some recent computational data that is not not yet in the paper. So first, what is resemblance? I take two polynomial f and h. Then we say the resemblance of h, f to h is b of f minus h. So for example, if I look at f of 5 and you f5 and then you took x squared and x, then their resemblance is just a b of x squared minus x. So you simply just plug in all the values and see how many different distinct values there. In this case, there is 3. So their resemblance is 3. So our idea is we want to consider this notion. So if I have a function in Fq, I want to consider the minimum f comma h, where h belongs to all the functions with a certain property p that we are interested in. And then we think this will be a way. This is a way to quantify how far is my function f from having this property p. So in this talk here, we are considering something I call the permutation resemblance. I denote it by p as f, is when I take this property p to be permutation. So if I fix f, then I look at minimum resemblance f comma h, where h belongs to all the permutation on that set field. So this is the definition I just covered. But most of the time, it's more useful to consider equivalent version. That is, you can do the change of variable. You can write f minus h as a negative g, and then it's equivalent to this one, minimum vg such that g plus f is a permutation. So in other words, I have a function f, not necessarily permutation, but I want to add something g to it so that the overall is a permutation, and that g has the least possible image. So first I comment that it is not equivalent to any other known quantities concerning a function's bijectivity. So for example, b of g, I'll give you an example later. And imbalance, that was like a collection thing, and the ambiguity and deficiency. And also, if you're thinking about this definition, then we can easily look at the trivial bound. So one extreme is when your f is already a permutation, then period f is just f comma f, so you have f minus f is a zero function, so you have one function. So then in that case, period is 1. And another extreme is f is a constant, then period f will be a constant minus any permutation, so then period is good. And so in our theory paper 2 years ago, we have a non-trivial bound for the things in between. Okay, so here is an example. So I take f5, and this function is very simple, just 0 sent to 0, and 1 and 2 sent to 2, 3 and 4 sent to 4. So overall, the image size is 3, df is 3. And this one, we can show that df is 2, because I can turn this f into a permutation by adding this two-value function g, so that corresponds to this 2 here. And how does this work? So g will take everything, g takes 0 to 4 to 0. So if I do f plus g, then overall I still have this image of g, image of f. And then if x is in 1, 3, then g will take these to -1. So in this way I cover the missing 1, 1 and 3. So overall g plus f is a permutation. So, however, notice that, well, x squared is also almost 2-to-1 function, meaning if you draw the picture like this one, it looks very similar. So it has the same VF and also the similar preimage sizes. We can show that P res x squared equal to 3 over F5. So this shows that P res is not equivalent to VF or any like preimage sizes. Okay, so here comes the main part of today is I want to talk about computation aspect, about how do I compute this periods, this quantity. Because this is non-trivial because you have to think about all the permutation and there are 2 factorial ones. So I want to use this equivalent. I want to use this equivalent definition. So I fix f, then we want to find a function g such that g plus f is a permutation and bg is as small as possible. And our approach is we turn it into an integer program. And it is actually a binary program. So in this program, I have x variables and y variables, but all of them can only take 0 and 1 values. And due to the time limit, I have to skip why, how do we get that? But if you're interested, anyone is interested, I'm happy to explain afterwards. But the point is a feasible solution, so meaning anything that satisfies these constraints, any solution corresponds to a set of function g such that g plus f is a permutation. And all such g that correspond to the same solution will have the same image set. And that image set is captured by these y variables, captured by these. And so an optimal solution, meaning it is feasible and also have the minimized this objective. This objective value is when it has minimum number of image g, so that is what translates to this sum of y variables. Okay, and then so we run this computation for x squared. So we use the magma for algebraic computation, and we use Gurobi to solve the integer program. So Gurobi is a commercial software, but it has an academic license. And so what I list here is for prime p, but we also have prime powers result. So you can notice that this thing actually grow pretty slow, and in fact my conjecture is I think we can show that PUS x squared is probably upper bounded by log 2q, but it's been several years, I still unable to prove it, so I think it's a pretty difficult question. And also, it is not completely monotone growing, so it has a weird drop. So for example, here, 53 to 251, it has been 5 all the way down, except one value, 103, dropped to 4 again. And we also observed this long time ago, but we are unable to explain why is that so. And then just a quick remark, in our paper, we only go up to 343, but very recently we use a newer Gurobi and Boise State computing cluster, and then we get the other three new values, and the longest one took 8.5 days. Okay, and this is what I present is my first integer program, and there will be another one next. So next I want to talk about application to this quantitative permutation resemblance that is in constructing permutation with low differential uniformity. So so the background has been showing several times in this conference so far, so I will go slightly faster here. So first of all, I fix a polynomial f, and then I pick any a and b. Then we define delta ab as the number of solutions to this difference polynomial. And then differential uniformity of f is the maximum of these guys. We'll consider all the a, b. And then we know that you want this, so I will call it du from now on. And so we want the du to be as low as possible because they have application in cryptography. And then we have seen the optimal object in characteristic 2. These guys are APN functions, so but in characteristic 2 you can get du equals to 2, as for example like x cubed. And in odd characteristic, you can actually go down to 1 as the minimum. And for example, x squared, these guys are coplanar functions. So this is why I was computing PUS x squared, because later on we need the application using a planar function. And we know that the most desired are those functions with both permutation and have the lowest du. But these functions are pretty rare. So in odd characteristic, it's easy to show that a planar function can never be a permutation. And in even characteristic, we have this famous big APN problem is prove or disprove the existence of APN permutation for f2 to the e, where e greater than 6 is even. So the next one would be f2 to the 8. And so since the perfect one is so rare, so what we are trying to do here is we are interested in constructing permutation with near optimal du. So it has low, but probably not the lowest. And there are a remark that there are also many other research is optimized du, but not necessarily permutation. But we are doing other way. We make sure it's permutation, and we see if we can get it low. So the reason why we think PUS is helpful to construction is because of the following theorem. So we can show that if I have two functions f of g, then their du g plus f is upper bounded by the expression by du of f and some expression about vg. So in particular, if I take vg to be as low as possible, like t plus f, then we could have this upper bound of delta g plus f. So the idea is that we start with the non-planar function of planar function or APN function, such as x squared. Then we know delta f is 1 or 2. So then this this would just be 1. Then I look at every function in this set. G plus f is a permutation, Bg is a P equals f. Then these guys, all these permutation will have a du bounded above by this expression. So that's the idea. And then so we found a way to compute du also with the integer program. And the idea is I want to think about a function as represented by a 0, 1 square matrix x. This x is q by q, so indexed by the elements of fq. And for a position xij is 1 if and only if f sends j to I. So in other words, if this function f is a permutation, if and only if x is a permutation matrix. So with this notion, we can actually write delta AB, so the number of solution to the different polynomial in this sum of quadratic 0, 1 variables. And the reason is because if J is a solution to this formula, if and only if I have Fj equal to I, so then this guy is 1, and Fj plus A equals to B plus Fj equal to I, so then this guy is 1. So if both of them is 1, then I make 1 count. So, okay, so this, so with this notion, we can transfer this problem to this optimization problem. So to find a permutation with the best du, we need to solve this minimize over all the permutation metrics, maximize the expression delta AB. So when I found this, I was very excited. I thought, oh, I can solve the if I'm a good computer, I can solve the behavior problem. But of course, it's not so easy. This integer program is quadratic because it has quadratic constraint, and so it has a q squared x variables. By x variable, I mean this is x. So computationally, it is impractical for q greater than 19. But the nice thing is we find out that if we solve TRES at first by my first integer program, and then we retrieve the search within these permutations that are produced by my solution, then we can, on average, we only need big O of Q X variables. So we can actually do compute something more interesting rather than just 19 or 17. Okay, so this is what I call a two-step method. So the first step is we solve the TRES that we solve the first integer program, and then we obtain not only the optimal value TRES, but I also get a set of permutation in this format G plus F, where even G is something the fix that we know. And then the second step is the DU step is within this set of permutation I obtained from the first step, we solve the quadratic program and to find one that with the best DU. So in our paper, we have this computation result by a slightly older version of Groby back then. So first, for APN function over even Q, in 64, we test X2, and this APN function, we both got 60. And then for 256, we test X cube, and we got 80 permutation. But these are not necessarily optimized one, because to optimize the 256 is too long. But if you just cut it when it starts getting stalled, then it actually only takes 4 minutes to find this 80 permutation. And then for the odd characteristic, in our paper we have a result up to 49 using x cubed, x squared is the product function. But here I'm happy to share that recently we pushed the computation to 343. Use the newer version of Groby this year and on the computing clusters by Boise State. And we also added some improvement to my codes by the they have a new AI Guru bot. So I checked with Guru and improved my codes. So this improvement includes things like manually linearize the nonlinear constraints in my program, and then also remove the restrictions of the things like G0 equal to 0, because initially I thought that since this equivalence is sufficient to look for thing G that has no constant terms. I thought it would be easier because the option would be smaller. But then it turns out it may be slower in the integer program, so it's a bit counterintuitive. And another thing is we can also in the code we can also early terminate whenever we find a decent one, we stop, so it will not take too long. So for this, up to 73, we can go up to d equal to 4, optimize both stack. But then, starting from 79, the second step takes too long, so I just make it cut at whenever it's from d equal to 4, then we stop. So then in that case, we can push to 137, and then from 139, it starts getting too slow to find the 4du, so then we cut it 5du, and then we were able to push to 343. So the longest computation over this data was 211 and took about 5.5 hours. And so these are for odd, but for even Q, I also try to test the XQ or like APN function, but this recent improvement does not give a better result. So there's still a lot to do in the even case even for the computation. Okay, so here I have a key takeaway. We define something called PRES, and it provides more nuanced measure to the projectivity of the function over the finite field. And we show that PRES f and du can be computed using via solving integer programs. You can solve it and use the PRES x squared over RQ. We obtain permutation up to du up to 4 for q up to 137, and du equal to 5 up to 343. So there's a lot of future works in the theory part, and here I list some future works for computational. First, for even Q, we haven't tested much APN functions yet, so what I tested is only x cubed and the one I showed you. So there's a lot to test on computation even for the APN functions. And then also I want to continue the computation to PRES x squared for larger Q. And then also maybe for the optimization part, maybe we can improve some bounds for PRES or improve bounds for du that constructed in my second step. Okay. And here comes the last slide of the conference. So thank you, everyone.
Thank you very much for this very nice talk. Are there any questions, remarks? Well, I have a silly one because I'm far from what I do. And what about like testing with some exceptional permutation polynomials? Do you think that would give the something? Yeah, say that you have those which are permutation with extension of the base.
You mean like something that's already known for
permutation
polynomial?
Yeah.
It's a good question. So here, so here because I'm looking at v f minus h where h belongs to all the permutations. So if I already take the permutation itself, then PRES will just be 1. That would be not interesting in my computation.
No, I see, but to use it to see, for instance, you can see if they take a polynomial, see how far is it from in an exceptional. Right? You can.
I see what you're saying. I see. Oh, okay. Oh, so that misunderstood. Yeah. I haven't thought about it, but I think that would be interesting.
Very interesting talk, but I mean, you didn't show the polynomials. They are probably very active, right? A lot of terms.
The polynomial we found by computed. Yes. Yeah. So the polynomial I get, the result, the data I get will be quad body to quad body like this profile, and then I try to do Lagrange interpolation, and it's just a lot of terms. Yes. Yeah, that's the ugly one. Yeah, indeed, it's not a nice
one. Comments, remarks?
So Magma also implements integer programming, right?
What is that?
Magma.
Yeah.
Also has integer programming. So I was wondering if you find the Gurobi much better than Magma, or?
So I did not know. I did not know Magma has an integer program until
It's in the manual, you can just.
Yeah, until I already started using the Groovy, so then I just.
I see, because there is some work needed for the transfer from Magma to Groovy, right?
Yeah.
So.
But my Groovy is over using Python, so I was thinking to.
Yeah, but still they have to go from Magma to Python, right? So
Yeah.
There's still different things.
Yeah.
Thank you. Any more comments? Marks? Well, let's not expect the speaker and all the speakers.